The velocity of a fluid describes how fast a fluid is moving at a certain point in the flow. Velocity is denoted by a lowercase v, with an arrow on top to indicate that it's the vector quantity. But if we wish to know how much fluid is crossing a given area per unit time, we need to look at the total flow rate over that entire area. The rate at which a fluid is crossing a certain area can be described in two ways, by its volumetric flow rate, or by its mass flow rate. The volumetric flow rate of a fluid, through a certain area in the flow, is the rate at which a given volume of fluid crosses the area per unit time. It is described by the symbol capital V with a dot on top, to indicate the time derivative. In its general form, the volumetric flow rate is equal to the integration of the velocity vector dotted with the infinitesimal area vector dA. Recall that the dot product means that any component of the velocity vector that is perpendicular to the area vector dA is cancelled out. In other words, if the velocity vector v is tangent to the area dA, then the dot product of v dA is equal to 0. To simplify the equation, we first assume that the velocity vector v is always parallel to the area vector dA. This allows us to change the dot product of the two vectors v and dA to a simple multiplication of the scalar magnitude of v times dA. We can simplify the equation further by assuming that the velocity is uniform or constant over the entire area A. This assumption allows us to solve the integration in the equation for the volumetric flow rate as the simple multiplication of the uniform velocity v times the total area A. The units of volumetric flow rate is meters per second for the velocity units, times meters squared for the area, or meters cubed per second. So the value of the volumetric flow rate flowing through a certain area, such as a pipe's cross-section for example, is equal to the number of meters cubed of liquid that cross the area in 1 second. The mass flow rate of a fluid through a certain area in the flow is the rate at which a given mass of fluid crosses the area per unit time. It is described by the symbol small m with a dot on top to indicate the time derivative. In its general form, the mass flow rate is equal to the integration of the density times the velocity vector dotted with the infinitesimal area vector dA. Assuming the density is constant over the entire area A, which is a reasonable assumption for an incompressible liquid, we can take the density term out of the integration. Assuming that the vectors v and dA are always parallel, we can replace the dot product of the two vectors v and dA by a simple multiplication. Finally, assuming the velocity to be uniform over the entire area A, we can solve the integration as the multiplication of v times A. Hence, using the aforementioned assumptions, we can calculate the mass flow rate as being equal to the density ρ times the uniform velocity v times the total area A. The units of mass flow rate is kilograms per meter cubed for the density units, times meters per second for the velocity units, times meters squared for the area, and so we have kilograms per second for the units of mass flow. So the value of the mass flow rate flowing through a certain area, such as a pipe's cross-section for example, is equal to the number of kilograms of liquid that cross the area in 1 second. Suppose we had a Y-shaped tube with fluid flowing in from the bottom of the Y and flowing out through the two upper branches. Now let's define what a control volume is. A control volume is simply an arbitrary volume in space that encompasses a certain volume of fluid, which in this case is our fluid within the Y-tube. The control volume is surrounded by a control surface, through which mass and energy can flow into or out of the control volume. Under steady-state conditions, since the mass and energy within the control volume are unchanging, we can conclude that the mass flowing into and out of the control volume is the same, and the energy flowing into and out of the control volume is also the same. Hence, for a given control volume that is at steady state, we do not need to be concerned with what is going on within the control volume. We only need to focus on the mass and energy that is crossing the control surface at the inlets and outlets of the control volume. tanks A through H are interconnected as shown, and are all at steady state. Water is flowing into tank A, from pipe 1, at a rate of 10 kg per second, while it is flowing into tank B, through pipe 2, at a rate of 5 kg per second. Furthermore, tank C is being evacuated through pipe 3, at a rate of 17 kg per second, tank H is being filled through pipe 7, at a rate of 20 kg per second, and pipe 6 is closed. What is the flow rate, and direction of flow, in pipes 4 and 5? This problem can be made much simpler if we choose wisely where to place our control volume. Recall that at steady state, the mass flowing into a given control volume is equal to the mass flowing out of the control volume, hence the summation of all the mass flow rates into and out of the control volume is equal to 0. If we simply place the control volume around the entire system, then the summation of m.1 to m.7 is equal to 0, and we get an equation that has two unknowns, m.4 and m.5, which we cannot solve. On the other hand, we can draw a control volume around tanks F, G, and H, and obtain an equation for the mass flow into and out of these tanks, which is an equation in a single unknown, m.5. We can solve this equation with the sign convention that flow into the control volume is negative, and flow out of the control volume is positive. And so we have m.5, which is the mass flow through pipe 5, is equal to minus m.6, the flow through pipe 6, which is 0, minus m.7, the flow through pipe 7, which is negative 20. Note the negative sign here because the direction of flow is into tank H. And so we obtain the mass flow through pipe 5 to be 20 kg per second. Since this is positive 20, this means that the direction of flow must be out of tank F. Similarly, we can find the mass flow rate for pipe 4. In this case, let's draw a control volume around tanks A, B, C, D, and E, and obtain an equation of mass flow into and out of these tanks, which is an equation in a single unknown, m.4. And so we have m.4, which is the mass flow through pipe 4, is equal to minus m.1, the flow through pipe 1, which is negative 10, minus m.2, the flow through pipe 2, which is negative 5, minus m.3, the flow through pipe 3, which is positive 17. And so we obtain the mass flow through pipe 4 as negative 2 kg per second. Since this number is negative, this means that the direction of flow must be into tank B. In its most basic form, the principle of conservation of mass means that mass can neither be created nor destroyed. Hence, as we have seen before in our explanation of the control volume approach, for a control volume that is at steady state, the mass flowing into the control volume must be equal to the mass flowing out of the control volume, in order to satisfy the conservation of mass principle. In equation form, for a control volume that is at steady state, the conservation of mass principle can be expressed as the summation of all mass flow rates that are going into the control volume is equal to the summation of all mass flow rates that are going out of the control volume. Assuming that the velocities at all inlets and outlets of the control volume are uniform and parallel to the control volume's area vectors at these inlets and outlets, as we did in our discussion of the mass flow rate, we get that the summation of the density times the total area times the velocity at all inlets is equal to the summation of the density times the total area times the velocity at all outlets of the control volume. If we assume a single inlet and a single outlet for the control volume, we can drop the summation operator, and we now have the shown equation. Finally, for an incompressible fluid that has a constant density, we can cancel out the density from both sides of the equation, and we end up with the relation that the surface area of the inlet times the velocity at the inlet is equal to the surface area of the outlet times the velocity at the outlet. Water is flowing through a circular pipe section that has a diameter of 10 cm in location 1 and a diameter of 20 cm in location 2. The velocity at location 1 is measured as 10 meters per second. Assuming the velocity in the pipe is uniform, and parallel to the pipe's walls, what is the velocity at location 2? And what is the mass flow rate through this pipe? We start by applying the continuity equation between points 1 and 2, where the cross-sectional area of the pipe at point 1, times the velocity at point 1, is equal to the area of the pipe at point 2, times the velocity at point 2. This equation can be rewritten as V2 is equal to A1 over A2 times V1. We can then calculate the areas at 1 and 2, using the pipe diameters at these locations. So we substitute 0.1 meter for D1, and we find that A1 is 0.00785, and we substitute 0.2 meter for D2, and we find that A2 is 0.0314, and so we have V2 is equal to A1 over A2 times V1, and get a velocity of 2.5 meters per second at point 2. Next we need to find the mass flow rate through the pipe. The mass flow rate, m dot, is equal to the water density times the cross-sectional area of a location along the pipe, times the uniform velocity in that location. We can choose either location 1 or location 2 to calculate the mass flow rate. Shown here is the calculation based on location 1. So we have flow water times A1 times V1, which gives a mass flow rate of 78.5 kilograms per second,